All right, we'll keep moving on here with for us in the Changle and Bowles text. That's chapter 6, kind of this introduction to thermodynamics. One of the things we need to talk about here is this idea of perpetual motion machines, right? And the idea of reversibility. So, a perpetual motion machine is any device that's going to violate either the first or the second law of thermodynamics. Now, no actual device can do this. No real device or real process is going to be capable of violating either the first or the second law. Now, the reason this is kind of a big point and the point of discussion is prior to the maturation of the science of thermodynamics, people could propose patents or sell tickets to come see their perpetual motion machine. I remember watching one time a series, a TV series where they talk about all these different oddities and things. I'm not going to mention the name of it here, but it's one such instance they were talking about was this traveling perpetual motion machine. And this is 1800s or so, and come pay your nickel to come see our device that never stops. And apparently, it was set up in this tent and all these black velvet curtains, and this device just sitting on this black velvet covered pedestal, and it just this little spinning wheel that just wouldn't stop, kept spinning and kept spinning, and you could walk all around it, and there was nothing attached to it, and nothing up their sleeve here, and at any rate, I guess a couple of local scientists at one place it stopped. Um, One of them, I guess, distracted the guy taking tickets at the door, and the other one kind of snooped around and looked under the velvet and followed this string that was attached to the device and noticed the string was kind of pulsating back and forth and followed the string back. And I guess there's this little old man sitting behind this tent, just pulling the string, eating a sandwich. And they asked the man, "What are you doing?" And they said, "Oh, these guys came to town. They offered to they said they would just keep feeding me sandwiches all day long if I would just sit here and pull the string." Um, anyway, it's this silly little story about a perpetual motion machines. Such things don't exist. We've known for some time. Before we really understood thermodynamics, we knew you can't really have a device that just operates perpetually with no exterior influence. Here's a nice one. Here's is kind of a cool setup. Let's say I've got a pump, some sort of pump that pushes out high pressure fluid, maybe air. So like a little air compressor pushes out high pressure air, and we run that air through a turbine, and that turbine spins. I mean, these can be simple. It's if like I know sometimes the vacuum cleaners have a little rotating brush for pet hair. We saw my cat earlier in the previous video. We've got a vacuum cleaner that has a little brush that as it pulls air through this attachment that goes on your vacuum cleaner, it makes a little turbine spin, and that turbine drives a brush. So that brush can kind of on a couch or a chair, it can run this brush to help the vacuum suck up all the hair. So the turbines can be very simple. You run high pressure fluid through it that makes some things inside it turn, some fan blades or something of the like, or like a big paddle wheel, basically. And through that process, then you extract work and use that work to drive the pump, and also you return low pressure fluid back to the pump. So the turbine now spins the pump and pushes out more high pressure, and this loop just perpetuates perpetually. And again, we know that's not going to be able to operate perpetually. Nothing that's going to violate either the first or the second law, maybe both, depending on how you set it up. Another one of my favorite examples here. Hey, this would be great. I love this design. If you can figure out how to do this, you don't tell anybody. I always tell students, don't tell anybody. Call Steve. Call me. We'll figure out how to do this. We'll be rich. But I'm going to let you figure it out first because I don't think we can do it. But anyway, let's say, in most heat engines, you've got some like a nuclear powered reaction, or you got to pay for coal or natural gas to be your heat source up here to run your boiler. And some genius here says, hey, why don't we just take electricity out of the turbine? We'll take the turbine spinning shaft, we'll run a generator, and we'll also use that spinning shaft to run a pump. And let's just use some of the electricity off of this generator to run our boiler, to generate the steam to run our turbine. And it'll be great. It'll be fantastic. And I always do this. I say, okay, what's our system? Notice the system boundary is this gray shaded area here. Right? That's our system boundary. And I say, okay, well, what crosses the boundary? Let's do a first law analysis. What crosses the boundary? Well, you've got minus power out, and you've got minus Q dot out. And if this thing is operating steadily, perpetually, that has to be zero. Notice it's not zero. It can't be zero. I've got minus something else cannot equal zero. Two negatives cannot sum together to be zero. I think this is the Clausius statement that it's either the Clausius or the Kelvin-Planck statement that we can't operate in a cycle and have the only effect being transfer of heat to one body or from one body and produce a net amount of work. It's not going to happen, right? So anyway, hopefully that helps. These are examples of perpetual motion machines. As I was mentioning earlier, before we really understood thermodynamics, you could propose a perpetual motion machine to the U.S. Patent Office and pay the fee. And then you had 20 years where nobody else could do that thing. And you had 20 years you could figure out how to do it and make money off of it. And so the Patent Office was just inundated with these things that just couldn't happen. One of the first things they'll do today is just check it against the laws of physics. If you violate the first or second laws of thermodynamics, no patent for you. At least you're going to have to very clearly explain why you think your device is capable of violating either of those two laws. All right. So what prevents a device from being perpetual, having perpetual motion? What causes this? Well, what we call irreversibilities is really what drives that. And to understand irreversibilities, let's talk about what reversible means. What does reversible mean? A reversible process is any process that can be reversed without leaving a trace on the surroundings. Now, we always make this clear. This is the theoretical limit. And this is, we go to the physics store to buy one of these because these things don't actually exist. The physics store where they sell frictionless pulleys and smooth surfaces, right? Such things don't actually exist. A reversible process doesn't exist, but we do have some that kind of get close. But what it does for us is it says, hey, in the best case scenario, this is the absolute best you can get. It gives us a point of comparison. We know anything that claims to be better than the reversible process is absolutely garbage. And anything that claims to be the reversible process is, we're going to be very skeptic at best about that because, again, it just kind of serves as this highest bar. All known processes, anything you and I are going to try to do, should be considered irreversible. And we'll talk about that more why when we get into the second law. Let's talk about what causes things to be irreversible. What causes a process to be irreversible? And we call those irreversibilities. Well, the biggest culprit is often friction, right? Anytime you're taking motion and converting some of that motion into heat, any kind of mechanical energy. I'm doing work to my hands right now to give them kinetic energy. And by rubbing them together, some of that kinetic energy or some of that work that I'm doing to generate kinetic or to cause kinetic energy, some of that mechanical energy is now being converted into heat. I can never get all of that heat back into mechanical energy and back into work because friction is a non-conservative force. We would have learned about in the Physics 1 class, the idea of non-conservative forces, anything that causes mechanical energy to no longer be mechanical energy. Not all of that can get back to a mechanical form. Electrical resistance is kind of like friction for flowing electrons. That's as electricity moves through a circuit, Some of that mechanical work that is electricity gets emitted out as heat through the electrical resistance process. If I take a pure canister of nitrogen and a pure canister of oxygen, I open them both up and I allow them to mix together. I now have some, depending on the ratio, I have essentially air. And to get it back into a nitrogen and oxygen format to get them both purified, it's going to take a lot of work on my part. So that's an irreversible process. Chemical reactions at their core are going to be at least a little bit irreversible. Some of them are very close to reversible, but all of them at some level are, you're not going to be able to get all of them. Once you have some reaction occur, you're not going to be able to spontaneously get all of it back to its original state without doing some work. Right? Your textbook loves, I love this example. Your textbook gives an example about baking a cake. That's a chemical reaction process, which is irreversible. And the way they describe that perfectly is they say, well, think about this. If I go and bake a cake, I take some flour, some sugar, some butter, some milk, and some eggs, and I use that to make a cake. If I take that cake then and I grind it up, and I try to get it back into the original ingredients of flour, sugar, milk, eggs, um, oil, butter, etc. Right? If I try to get it back to its original ingredients, well, sure, I could grind that cake up and feed some of it to some cows. They're probably gonna like that. And they'll generate some milk, and I feed some to some chickens, and they're gonna generate some eggs, and use some of that milk to turn into butter, and and fertilize some wheat field and some sugar cane, and sure, I could I could get take that cake and I could turn it back into its raw ingredients. But it's to do that, it's going to take some effort on my part, and it's also going to take some input from the sun, from solar energy, a very what we will call a very low entropy form of energy or source of heat. Um, we'll be able to get those ingredients back to their original state, but not without leaving an impact on the environment, right? That's the thing about, I didn't mention this when I defined reversible process. Reversible process is anything that can be reversed without leaving a trace on the surroundings and the system, both. If I can get the process back to its original state and not leave a trace on both the system and the surroundings, then that's reversible. Things that are irreversible are either going to leave a mark on the system or leave a mark on the surroundings or a little of both, but we're never going to be able to get both the system and the surroundings back to their initial state. One or the other is going to be permanently changed. It's irreversible. We can't go back to the initial state for both, for the entire universe. And once we began to understand that, that really helped us formulate what becomes the second law. All right. I think I'm going to stop this video here and we'll pick up the next video. Yeah, so I'm going to pick up on the rest of lecture 16 on the next video.